Okay, the next section 6.6 is on inverse trig functions. So we're going to evaluate some of these for sine. We'll graph the other inverse trig functions as well, cosine and tangent, and we'll do some compositions. Okay, here's a good look at the graph of inverse sine. Now, the graph of the regular sine, we know, goes like this. Right, it's a sine wave. So the inverse is always the reflection of line y equals x. So we would reflect over line y equals x, and we get this other function here that they have graphed, which would look really like this if it kept going. But the reason we cut it off here and here. And the reason why is because otherwise it's not a function. If this keeps going and this keeps going, it's not going to pass the vertical line test, which doesn't help us because when we stick in one value for x, we get an infinite number of values for y, which doesn't help us any. So that's why we cut this off, and we end up with just this function here. Now, the really important part is that you know the domain goes from -1 to 1, and the range goes from goes from negative pi over 2 to pi over 2. Now, that's on the formula sheet, so you don't have to memorize that, but that's really important. Another way to get it, like I said before, is that you can look at this as being the reflection of the regular sine, and the regular sine function has a domain of -infinity to infinity and a range of -1 to 1. So what you can do is look at switching these, because that's what you do for inverses. That's why the -1 to 1 ends up in the domain. And just remember that the range, which is the domain of the original, has to be restricted. So you have to do one cycle basically, or not really one full cycle, but from -pi over 2 to pi over 2. So here's that information. X is going to go from -1 to 1. Y is going to go from -90 to 90. Therefore, the domain and range is as follows. Now, you might see this arc sine quite a bit. A lot of books use arc sine instead of inverse sine. That's what we're going to use in web work as well. So I like to write inverse sine like this. But keep in mind, these are the exact same function, just written with a slightly different notation. I'm sorry, arc sine. Okay, so here's a couple of example problems. We're going to try to find the inverse sine of these. Now, I'm going to try to use the calculator first. So I'm going to do inverse sine of -0.5 and see what that gives me. It gives me -30 degrees. Now, another way to do this is to call this equal to some angle. I'm going to use theta, because that's what this really means. It really means the sine of theta equals -1/2 if you switch the domain and range. So the question is, on the unit circle, where does the sine equal -1/2? Well, the sine of -1/2 is down here. And so it's at either of these two spots, which we have to use this spot here because the range has to be between -90 and 90. So we're looking at -30 degrees, or I'll use -pi over 6 for the answer for part A. Next one for part B, we can do the same thing. Call this some angle theta, and then write this as the sine of that angle equals square root of 3 over 2. So the question is, where does the sine equal square root of 3 over 2? That's up here, because the sine is the y value. And we have to be between -90 and 90, so we have to be over here, because that's our range for the inverse sine. And that would be a 60-degree angle right here, or pi over 3. And the last one, if we call this equal to some angle, the sine of that angle is equal to 2. We know the sine of no angle equals 2. Sine can only go from -1 to 1. So we know it never reaches 2 up here. Therefore, there is no answer to this, so we would say no solution. Okay, so if you're going to sketch a graph of the inverse sine, I like to write this as inverse sine of x. I like to look at what the domain and range are. So the domain is -1 to 1, and the range is -pi over 2 to pi over 2. So then I can make an xy table pretty quickly, and I'm going to rewrite this as the sine of y equals x. So I'm going to use this to make a quick table. So I'll look at the y value of -pi over 2, and if I plug that in on the unit circle, -pi over 2 is down here, the sine is -1. If I plug in a middle point of the range, like 0, plug that in, sine of 0 gives you 0. And if I plug in the endpoint of this range, which is pi over 2, up here, the sine value is 1. So that goes from -1 to 1, as we know, and from -pi over 2 to pi over 2. And so I can enter that point, and this point, and then this is what the inverse sine looks like. Okay, you can also graph this on your calculator, obviously, or in Desmos. I'll just show you the calculator real quick. If you do inverse sine of x and graph it, make sure you're in radian mode. You'll see this. I can zoom in. In fact, I know my domain and range, so I can go from -2 to 2, for example, because I know it only goes from -1 to 1. And I can go from, also from the y's from -pi to pi, because I know it goes from -pi over 2 to pi. So I can graph that, and that'll zoom me in a little bit and show you the same exact graph. But there's the inverse sine function. Okay, now it's the same thing for inverse cosine, as I just showed you for inverse sine. So we've got inverse sine, here's inverse cosine and inverse tangent. And they follow the exact same thing I just said about sine. So the cosine, normally looks like this, but when you reflect it over the line y equals x, you get this function here, which keeps going on forever. Well, we have to restrict the domain, so we actually have a function. So what we do is we restrict the range from 0 to pi, right here. So here's the arc inverse cosine. Goes from 0 to pi for the range. Domain still -1 to 1. And tangent, we know, looks like this. And so if you were to reflect that over the line y equals x, you'd end up getting a function that looks similar to this. And it would keep repeating. But we have to also restrict the range on that one because otherwise it doesn't pass the vertical line test. So that's what we do for that one as well. So there's the inverse cosine, inverse sine, and inverse tangent, the three functions we're looking at today. Here's the summary of information that I put in the formula sheet that you can use if you forget the domain and range of each of these. I'll just do a couple more examples and call it good then. For A, that's the inverse cosine of square root of 2 over 2, which I'm going to say equals some angle theta, and then I'll switch that to cosine of theta equals square root of 2 over 2, and say where on the unit circle is the x value equal to square root of 2 over 2, and that's at 45 degrees because that's square root of 2 over 2 comma square root of 2 over 2. So the x value there at 45 degrees, that'd be pi over 4, or 45 degrees. Next one, I'll call this equal to theta because inverse trig functions are always angles. And then I can write cosine of theta equals -1. And so where does the cosine equal -1? Well, that'd be here at pi. So the answer to this, the angle we're looking for, is pi. C, if I call this equal to some angle, and if I write it by switching domain and range and write regular tangent of theta equals 0, well, keep in mind tangent's really sine over cosine. So if we're looking for where this equals 0, we need where the sine is 0, and that happens at 0. So the answer to this angle is 0. And the last one, if I call this equal to 0, theta I mean, for an angle, I can write tangent of theta equals -1. So if we're looking at where the tangent equals -1, we need a spot where the cosine and sine are the same, but one of them is negative. And we have to stay between -90 and 90 because that's where the tangent range is. So that'd be down here at -45 degrees because we have square root of 2 over 2 comma negative square root of 2 over 2. And so if we do tangent, which is sine over cosine, we end up doing y over x, which is going to end up giving you -1 because they're the same, but one of them is negative. So that angle we're looking at is -pi over 4. And I guess the last thing is tangent and inverse tangent undo each other. So this is going to be -5, and this is going to be 5 pi over 3. And this would be pi, but the problem with this one is the inverse cosine, the range, or the domain rather, is from -1 to 1, and that's 3.14. So I can't stick that into the domain of the inverse cosine. So that's going to be an undefined value right there. So there's no solution to this one. But as long as you stick in a number that's in the domain of the regular inverse sine function in these cases, and then for this one, you got to make sure that this angle that ends up being in the domain for inverse cosine, which it is, because it's a really small number, which is between -90 and 90, or between -1 and 1, then it will work. So they'll undo each other almost all the time. Just make sure you're careful about the domain and range, and you'll be all set for the well work homework.